So we left off last class talking about this binomial distribution, right? So we'll start kind of reviewing that. The video I kind of put up on YouTube covers the next thing we'll talk about. It's not a lot of us here today, so I'll probably pretty kind. But I will kind of go through that a little bit quicker, kind of having that out there. That's kind of the reason why I'm putting those out there and wanting you to watch those before we talk about a subject. You've got a Connect assignment due Wednesday and Excel due Monday, right? And then our exam will be Friday of next week. So I can see that some of you haven't kind of started the Connect, which leads me to believe a lot of you probably haven't started the Excel either. I highly suggest getting on that as soon as possible. I put those out, plenty of time to the due date so that you kind of work on them, not save it until the couple days before. It's a lot harder for me to answer questions and kind of help you out with those the day or two before, as opposed to if you can come to me earlier. Yeah.
Is it on Wednesday or Friday?
The exam. Oh, sorry. Your Monday, Wednesday class. Yours is going to be on Wednesday. Sorry.
In class.
In class. Yeah. Sorry. All my other classes there are Friday, and a couple of them have exams as well. So, sorry, misspoke on that. Our exam is going to be Wednesday, right? So I don't, that Connect assignment is due the end of the day Wednesday, but I don't suggest waiting until then to do it, because then you've got the exam going on at the same time. That doesn't sound like a very good idea to me. Okay. Any other questions? Thank you for asking about it. Any other questions from you before we jump into things today? Yeah. So I will give that to you on exam day. Yep. And we'll talk a little bit more about the logistics of the exam Monday. And we'll be doing some review in class on Monday. We should be able to get through all the new, maybe I might save a little bit of it today and end a little bit early, but for the most part, we're going to be doing review all day on Monday. Okay. Yeah. So we'll talk more about it Monday, but it's primarily multiple choice and potentially like a little bit of short answer where you kind of show me your work with that. So we'll kind of give you the breakdown of it Monday, so you have a better idea what it looks like. Yeah.
So on the exam, are we going to be get asked questions about like Excel formulas and stuff like that, or is it just like a handwritten?
I would say to get a good idea about what the exam's going to look like, those practice exams are a pretty good idea. I won't ask any specifics about Excel because I don't want you to have to memorize all of that as well, when in reality it's pretty easy to Google search it, and when you pull up open Excel, it usually like reminds you of the things you need as well, right? So I'm not as concerned that you have rote memorization of those exact, so no, I won't ask that. Other questions? Yeah.
We want to have like a note card.
So I'll just give you that formula sheet. Yep. So that'll be kind of you'll have all the formulas that we've ever used. We'll go over that a little bit more on Monday as well, and kind of how potentially you can study it and make. Actually, I'll try to do it at the end. I'll show you guys something on the formula sheet, and I'll point something out that'll be helpful for the exam. Okay. All right. So let's dive into the material. We'll try to get through all that, and then at the end, like I said, I might talk a little bit more about the exam, show you some things on the formula sheet. But we broke this down last class that we have this variable that has two outcomes, success or failure, right? And the probability of success of any one trial is the same across all of them. So it's like I flip a coin 100 times, my number of trials is 100. Probability of success on any one trial would just be 0.5, right? Probably I see heads on any one coin flip is 0.5. And then I'm going to use this formula to find the probability of different outcomes. So if I flip a coin, I'll make it easier. Let's say I flip a coin 10 times. Right? The possible outcomes I could see 0, 1, 2, all the way down to 10. We're going to use that function to essentially tell us what's the probability this random variable x is equal to 0. Write that number down. Use that function again. What's the probability x is equal to 1? Now x is 1. Plug in the formula, write that number down. So essentially, we can find the probability of any of these possible numbers of successes. Okay. So a couple of things I don't remember if I mentioned last class, but it'll help us out. And we don't have to know exactly why, but 0 factorial, we said the factorial is like start at this number and multiply down to 1. 0 factorial ends up being 1. So I actually got interested thinking about how I was going to teach this, and I looked up some video and wasted like 40 minutes of my life last night. I shouldn't say it was wasted, but I was watching a guy go through the mathematical proof behind why this is. And even I was like, this is a little bit, well, I don't know how to boil this down or condense this to make sense, right? So I would say, for the sake of this, probably in other math classes, maybe you've heard like, if you take anything to the 0 power, that's also what? 1. Can you give me a great intuitive reason as to why? It's just one of those rules of mathematics that kind of basically make things work out kind of pretty well. And some of the idea here is if you do this n-1 idea, you know, you end up with like 0 minus 1 times, you know, 0 or 0 minus 1 would be -1. I went down this rabbit hole. It's really difficult without actually looking at the line by line mathematical proof as to why this is. But for the sake of what we're going to do, this is a mathematical rule that we know can be proven by someone over in the math department, right? So anything we're doing here, we don't have to deal with negative factorials, right? Because what's the lowest number? I mean, what's the lowest n we can see? The number of trials, 1. What's the lowest possible number of successes we could be interested in? Something can't happen in negative time, like in the sense that like either the very lowest it just doesn't happen, which would be 0. Right? So the only time we really have to worry about the 0 factorial thing is if we're looking for the probability of 0 successes, which we might be interested in. So we'll use this formula. So the first example I have here is kind of using a coin flip example, but it's not going to be dealing with a kind of boring coin. It has some bias to it. So instead of 0.5, the probability it comes up heads is only 0.4. Right? So I'm going to flip this coin 10 times, and I want to find the probability that it comes up heads 4 times. Right? So what's my number of trials here? Yeah, I'm just flipping the coin 10 times. Probability of success, only 1 coin flip. It's a biased coin, it's 0.4. And then what's my X value? Well, that's the probability that I'm trying to find, right? What's the probability I see heads come up 4 times? So my X is going to be equal to 4. From here, it's a matter of writing this out, right? So n factorial, oops, I'll show this, there we go. N factorial, our n is 10, x factorial, n minus x factorial, probability of success, the x power, 1 minus the probability of success, the n minus x. Just writing that out and plugging in my numbers for n, x, and then b. It's a simple, you know, that's going to be the process we use every time. Now, a couple things to point out here just in practice. If I try to enter this all in my calculator one time, it's a little bit tricky. But like, there's some really easy math here, right? Like, I can rewrite this to be 0.6 to the 6th. I hopefully can do this math in my head, right? 10 minus 4, 1 minus 0.4. Just make it a little bit easier when I go to enter in my calculator. I don't need a bunch of more parentheses. Or why add more parentheses if I don't need it? It's just easier to forget one, right? This is going to be the guy that's a little bit harder to deal with, right? So I would write this out. I mean, I think I mentioned last class. So every calculator should have a factorial button on it, an exclamation point. Usually it's under, you know, a math button or a PRV or math, go over the probability and then down. If you can't find it, you can still write it out and enter it into a calculator. So in this one, right, 10 times 9 times 8 times 7, all the way, I'm going to run out of room, all the way down to 1. 4 factorial is 4 times 3 times 2 times 1. 10 minus 4 is 6. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Well, notice if I write this out, instead of entering all this into my calculator, everything past 6 cancels there. So I've just got 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times. I can get that entered in my calculator relatively easy. And then once I have that, multiply, I got the rest of the equation as well. But a lot of stuff will cancel. Now it's probably easier, especially as I start to work with some larger numbers, to find that factorial button on your calculator. I would suggest doing that far in advance to next Wednesday, right? So start, try to find it over the, tomorrow or Friday. If you can't find it, send me an email. I'll probably Google search whatever to ask you what calculator you have, Google search it, and tell you how to find it. So maybe try to use Google first before you come to me. But usually, like I said, it's under like a math or a PRB kind of button on your calculator, depending on what kind of calculator you have. But really, once we identify the three things we need, it's really just plugging those values into our equation and sometimes dealing with these pesky factorials. So that's all we did here. All right, I just plugged all my values in, right, and then my equation or in my calculator should be about 0.25. So the idea behind what we're doing here is, if I flip a coin 10 times, I'll make it easier, right? If I flip a coin 100 times and I have a regular coin where the probability it comes up heads is 0.5, what do you think is the most likely outcome for the number of heads that I'll get out of those 100? 50. Yeah, 50. Right? So what did you do intuitively in your head there? You found the mean of that binomially distributed, there we go, variable. Okay. What you really did was just you took the number of trials and you multiplied by the probability of success. 100 times 0.5 gave you 50. So here, if we wanted to find the mean or the most common number of outcomes or the number of successes we'll see flipping this bias coin, 10 times 0.4, the most common outcome would be 4. So the outcome or the number of successes that will be the most likely for us to see will be whatever that mean value is. So if I'm thinking about, before I show you, you could come up with all these different possible 0 through 10 and the probability associated with each one. If I'm thinking about the different possible outcomes for X, I just said that 4 is the most common, which if I'm thinking about putting probabilities on this y-axis, that means that if I were to do this bar chart, this probability distribution in a visual form, this should have the highest bar, right? Whatever that mean is should be the most likely outcome for us to see. And then, the probability of seeing only 3 is a little bit lower. The probability of seeing 5 out of these 10, 6 out of the 10, 7, 8, right? And this kind of makes sense. As we move away from that mean or that most common response, well, seeing all 10 of the 10 coin flips come up heads should be very, very unlikely, right? A really small probability. Well, why? Because it's further from that kind of most common outcome, or that average outcome. Okay? So when we find the mean, we know that number of successes will be our most likely outcome. And that is we move away in either direction, looking for the probability of 0 or 10 is our number of successes there. As we move further away from that average, the probabilities will be declining. Okay? We'll kind of exploit this here in a little bit as well. So let's say I have a different example. Right? I've got this Wall Street Journal that says, looking at the data, if you chose a person at random, the probability to have a college degree is about 0.3, right, or 30%. Okay. If I then ask 5 people, right, 5 adults, what's the probability that 3 of those 5 have a college degree? Right? So I'm going to have the same sort of setup, right, but different values here. So what would my number of trials be here? 5. Yeah, I'm asking 5 people. Right? What's the probability of success in any one trial? 30% or probability of 0.3. Right? And I'm interested in finding the probability that exactly 3 have a degree. So my X is 3. Okay? So once I've identified those 3 pieces of information, it's really just a matter of plugging those values into that equation. Like you said, on a formula sheet, you'll have that formula in front of you. You start writing out whatever your n is, 5 factorial, whatever your x is, 3 factorial, and just kind of plug all your values in there. So working through some of these on your own. So there's a couple problems on the Connect. Maybe trying to be able to reproduce these answers on the slide. Getting used to entering this equation into your calculator. You want to get some practice doing that because it's not always the easiest. So one thing I sometimes suggest is breaking it down into parts. Instead of trying to put this all in my calculator at one time, maybe first I find this fraction, write that number down. Then I find what 0.3 to the third is, write that number down. And find what this is, write that. And now it's just this times this times this. Okay? So I can kind of do some intermediate calculations so I don't have to put it all into one line on my calculator and like have a, potentially make some order of operation there. Okay. Any questions over anything we've done up to this point? Yeah.
So on the coin flip example,
Yep.
if we go back, so if the probability had been 0.5,
Yep.
would the answer just have been 0.5?
So I think what you're asking, if the probability is 0.5, then with the probability of seeing 5 of the 10,
Okay.
is that what you're?
Yeah, I guess.
Yeah, so not necessarily, right? So think about it this way. If I had, I'll tell you why those two things won't necessarily be the same. So if I had something with had a probability of occurring of like 0.9, so let's say I have 10 trials, my probability of success is 0.9. Well, what's the probability that I see exactly 9 of them? Well, it's going to be a likely outcome, but the probability isn't going to be as high as 0.9, right? Even if on any one trial the probability is 0.9, out of 10, the probability that I see 8 or 10, right, just a little bit off that, still pretty likely, right? Not as likely as seeing 9, but still pretty likely. So the probability wouldn't be as high as, so this underlying probability, just because you're kind of looking at that mean, they don't have to line up at all. And as we work through more of these examples, I think it'll be a little more evident. Actually, in this next one, right? So sorry, does that?
Yeah, yeah.
All right. Any other questions before I kind of jump back to this example? Okay, so this one's a little bit trickier because I think it's not as intuitive, but we know that we have this equation here. What would be out of 5 people, what's the expected number of people with a college degree? Out of 5, what's the expected number of people that have a college degree? Remember, underlying probability of success is 0.3. If it was 10 people, it'd be pretty easy. If I had 10 people here, the probability of success is 0.3. The expected number of people out of 10 that have a degree would just be 3, right? It's easy if I keep it at like these 10s and 100s. Out of 5 people now, right? I just can plug those values in, so it's not as easy to kind of visualize or intuitively think about, but this equation is pretty easy to use to find the mean of that binomial variable. So out of 10 people, we expect 3 to be the most common number. Out of 5, 1.5. Now, this is kind of weird because we have a discrete random variable here, right? We can't actually see 1.5. So anytime the mean is like a decimal, what that's really telling us is that, kind of give a visual to it, the responses of 1 and 2 are going to be the most likely outcomes, right? The average is 1.5, we can't see that, but we can see 1 or we can see 2. So these would be the most likely outcomes. And then as I move further away from that mean, well, the probability of seeing 0, that would be a little bit lower. Probability of seeing 3, a little bit lower. 4, a little bit lower. 5, even lower. Right? Moving away from that mean, the probability of seeing that number of successes starts to fall. And that kind of makes sense. If on average, out of 5 people, 1.5 have a college degree, well, the probability of seeing 2 should be still pretty likely. 3, a little bit less likely. Seeing 4 of them, a lot less likely. Seeing all 5, even less likely, right? So we just found this was 0.13. Okay. I could do this exact same thing and say, okay, what's the probability that exactly 4 people have a college degree? Nothing really changes there, except for, right, I plug that 4 in. So I've kind of shown you the answer, but to get kind of at this idea, I kind of already showed this to you. I'm going to say some, so if you're paying attention, it should be an easy question to answer. We just found the probability of 3 out of these 5 having a degree is 0.13. So which of these answers has to be the probability that exactly 4 of them have a college degree? Based off of what we said, we're moving further away from that mean of 1.5. You should be able to quickly identify which of these 4 answers has to be the probability that x is equal to 4. Okay. So I'll give you some time to get your iClickers out and get them ready. You don't even have to do the calculation here, right? You actually should, based off of the principles that I've just kind of been going over, moving further from that mean. We know the probability of seeing exactly 3 out of 5 is 0.13. what is the probability of seeing exactly 4 have to be, of these 4 responses? Let's give it a little bit of time to think about it here. All right, I think everyone's got an answer. And if you don't have an answer in, take your best guess now. It's got 23 of us here today. It's not boding well for the upcoming exam. So I think I accidentally showed you another slide, which if you're paying attention, that's part of it, right? So which one of these do I know have to be the probability that I see 4 out of the 5 have a college degree? Nobody wants to take a guess? A, right? I know it has to be A. Why does it have to be A? Right. Exactly, right? If the average rate is 1.5, I'm moving further from that average. So as I move further from it, those outcomes just become less and less likely. If I know the probability of seeing 3 is 0.13, well, now I'm looking for a number of successes even further from that mean of 1.5. So I know it has to be less than 0.13. The only value up here that's less than 0.13 is A. Now I can go ahead and plug these into that formula and come up with exactly that 0.02. Like if I didn't give you that as a multiple choice, you would have actually had to plug in x is equal to 4 and kind of go through enter this into your calculator. Right, but just looking at knowing that principle that as I move further from that mean, right, the probabilities are declining, I could have kind of picked from those 4 options the one that had to be correct. Any questions on that idea? So like I said, here's another one. Might be good to make sure you can, there's not a lot I can really teach once I get to this point, right? We can identify n, x, and p. We've got this equation, it's just writing it, plugging our numbers in. At this point, I can't really, I guess if you want to during office hours, I can come in and I can teach you how to make sure you're using your calculator correctly. But in terms of like in class, I can't really show you, how to use that calculator, maybe pick up mistakes that you might easily be making. So actually working through these kind of on your own is a good thing to make sure you can use your calculator or enter that formula into your calculator. Okay. What if I ask for the probability that x is equal to 5? That probability would be pretty close to 0, right? If going from 3 to 4, it falls from 0.3 to 0.028. Going from 4 to 5, it probably gets really close to 0. Right? And the only difference there is we would plug in, instead of 4 for x, plug in 5. So what if I instead asked you for something like this? What's the probability that at least 3 of these 5 people have a degree? So maybe I want to make sure this sample is kind of overrepresented of people with a college degree. So I want to ensure that at least 3 of them have a degree. So then when I start using this sample to find, other things, I make sure that I've got the kind of breakdown of college versus non-college that I want. So if I want the probability that x is greater than or equal to 3, we kind of talked about this idea. I think I introduced it, or maybe I did. But all these outcomes are mutually exclusive, right? I either see exactly 3 out of 5 have a degree, exactly 4 out of 5, or 5 out of 5 have it, right? I'm seeing one of them and only one of them as the outcome. So all of these are mutually exclusive outcomes. So if I think about all the outcomes that fit this criteria, I can simply A or B would just be the sum of the 2 events because there's no intersection, mutually exclusive, right? It made our life easier when we wanted to find unions. Well, this is really a union in disguise. It's saying what's the probability x is equal to 3, or x is equal to 4, or x is equal to 5, and that 4 is our union. So really what we're saying here is, I want to take the probability x is equal to 3, plus the probability x is equal to 4, plus the probability x is equal to 5. Well, I stop there. Right? The most I can see is 5 out of 5, right? I always know where I can stop, right? So my number of tries. Well, now I have to use that binomial equation 3 times, right? N and P are always the same, but it's for 3 different x values. Well, we've already done this. We found the probability x is equal to 3 was 0.13. probably x is equal to 4 was 0.028. Now it's just a matter of using it one more time, finding that probably x is equal to 5, and then add them all up. Okay? Now we said this is going to be pretty close to 0. If I actually go ahead and plug that in, it'll be 0.002. Right? So I can add these up. Oh, right, with that, probably the x is greater than equal. So this is just basically like, if you want to think of a non-technical way to remember it, anytime you're looking for like a greater than or less than, all you're going to do is find the probability of every outcome that exists or that fits that criteria and add those probabilities up. Right? So x is greater than or equal to 3, find probably x is equal to 3, plus probably it's 4, plus probably it's 5. That's all the possible outcomes that can fit that criteria.
If you were to do include 2 and 1, would that equal a total of 1 for the probability?
Close. You're thinking about this the right way, but what outcome did you forget? 0. Yeah.
So technically speaking, you could potentially do the opposite, the difference of 1.
Yeah, you're jumping the gun up. So I'll give you a good example of where this becomes really important. Right? So first of all, are we okay with this idea? And that has it in the slides here, but I'm going to show you an even better example, right? I could have written this as kind of 1 minus the outcomes that didn't fit the criteria, right? Or the complement. Well, I still would have had to use that binomial equation 3 times. So it didn't really save me a lot of work, right? But what if I had a scenario? Let's think. What do I want to do first? So I'm going to show you how to do the complement first. So let's say n is equal to 100. I don't know. It doesn't matter what the probability of success is right now. And x is that I'm interested in. Find the probability that x is less than or equal to 98. Right? Well, what are all the outcomes that fit this criteria? X could be 98. Plus the probability it's equal to 97, plus the probability it's equal to all the way down to 0. I can't, yeah, if I'm going to ask you all this on an exam, there's no way you have enough time to do that, right? It's impossible. But if we think about this as event A, I know that that's the same as 1 minus the probability of a complement. What's a complement here? X is just, there's only 2 outcomes, but how would I write this complement? Greater than 98? But what are the only outcomes that fit this criteria? Well, we're dealing with a discrete variable. So the first number that's greater than 98 would be 99. And the only other possible outcome with a number of trials of 100 would be x is equal to 100. So we could rewrite this as find the probability x is equal to 99 plus the probability x is equal to 100 and then subtract them from 1. So something that looks like it would have taken us forever to solve if we use that complement rule becomes a lot more feasible. Okay. Any questions on kind of how we would use that? And that becomes really important for the Poisson examples that we're going to talk about here in a second. I think at this point I want to show you one other thing. These factorials, I kind of already alluded to this, but sometimes you want to write it out. So let's say I want to find the probability that x is equal to 99 here. So n factorial would be 100 factorial over x factorial and minus x factorial, right? I'm using 198, or I said 98. Let's use that 99. Really highlight this. Okay. So let's say okay, use the complement rule. Now, how do I find these? And I've got the rest of the binomial equation, but for now, we're just going to focus on how we deal with these factorials. Okay. So the rest of the, this component is going to be in there. We're just going to ignore that's a little bit easier to deal with. We're going to focus on a problem, which is if you have, I don't know if any of you have found that factorial button on your calculator, but if you put in 100 factorial, it's going to yell at you and tell you, I can't do this, right? Overload or something like that. But if I write this out, right? 100 factorial. I'm not going to write every single number, but just start it. 99 factorial, all the way down to 1. And then 100 minus 99 is just 1. So 1 factorial is just 1. Notice everything from 99 on down is going to cancel. All this expression is equal to is 100 divided by 1. Right? So our calculator can't do that. If you try to put in 100 factorial divided by 90, it's going to yell at you because it has to calculate that factorial, and that button's just, or that number is way too big for it. Even like a TI 83, 84, it's capped somewhere off in the 60s, right? But, right, this is a good example where just because a machine can't do it, a machine can't critically think, it can only go through like this programmed kind of operation, right? So it can identify that there's an easier way to then simplify this. Now, there's probably computer programs that could recognize that, and that's, I think Excel kind of has one that's built into it, so it wouldn't run into these problems. But if you're trying to use that calculator, it doesn't realize like all this stuff can cancel. But if you write it out, it's a pretty simple equation. Okay. Any questions on this idea? Yeah.
I might be getting ahead here, but when looking at probability to get specific, like for example, that X is greater than or less than greater than or equal to 98. What if it said like greater than or equal to 50, but less than or equal to 98, like it's specific?
So there's not an easier way to solve them like that, but like let's say over here, right? I wanted the probability, just look at smaller numbers. If I want the probability that something like that, same sort of logic applies. I'm just going to add the probabilities of every outcome that fits this criteria. So what would the outcomes be that fit this criteria? X could be equal to 2, X could be equal to 3, and X could be equal to 4. And I could make it real complicated. Like we could do somewhere like, if I had like the larger numbers over there, I could say, what's the probability that X is less than or equal to 98, but greater than or equal to 2. Right. Well, then on one end, you have to use the complement rule. On the other end, you can just, but I'm not going to probably do that. But all right, if you really want to, you could really, combine a lot of these at the same time. I'm just trying to like single out some specific things here. But yeah, the same general thought process fits it, right? Because what outcomes fit the criteria? Add the probabilities of those different outcomes up. Any other questions before we keep moving here? All right, so we already talked about the mean for these binomial distributions. It's kind of intuitive. The variance is not intuitive. You could Google binomial variance proof, and if you think about using the general form of this equation, and you found like a weighted variance, like or a variance of a discrete random variable, you could go through every outcome, right? 5 minus the mean, square it, multiply it by the probability that 5 occurs. What's the probability 5 occurs? This function is going to give that to you. Right? Add to that the next outcome, deviation from the mean, 4, so 4 minus the mean squared, multiply by the probability that 4 occurs, which would be coming from this function. If we write this out without any numbers, just like the general form of the equation, what that will always simplify to is that the variance is equal to n times p times 1 minus p. So, like I said, if you don't believe me and you want to look up in Google, binomial distribution variance proof, you kind of look at it and try to follow through the math, but it always simplifies down to that. Okay? And it kind of makes sense, right? As the number of trials goes up, there's just more variation we can see. You think about flipping a coin 10 times, you can see the number of possible outcomes from 0 to 10. If you flip it 100 times, you can see anything from 0 to 100. Right? You have a much wider range of possible values. The standard deviation, same principle applies. If I want the standard deviation, I just do what? Take the square root, right? Nothing new here. Now, one thing that's kind of interesting to point out here is as long as my mean is above 1, which more often than not it's going to be. If my mean is above 1, what has to be true about the variance relative to the mean, I could say that the variance is always, so P is going to be something between 0 and 1. So I know that 1 minus P will be something less than 1. Here's my mean. To get my variance, I'm essentially multiplying the mean by 1 minus P, or by some value less than 1. So the variance will always be less than the mean. Now, if we end up with a mean that's less than 1, then it's a little bit harder to think about. But for the most part, all the examples we have, we're going to have a mean that's greater than 1. So the variance of this binomial distribution should always be smaller than mean, as long as that mean's greater than 1. I'm not like ask you that like the definitional thing, but just kind of pointing that out. So I like these visuals, even though it looks like it came out of like a 1960s textbook, but it's a real good, it was a nice, easy thing for me to be able to kind of explain a couple things to you guys. So if my n is 5 and my probability of success is 0.1, so relatively low probability of success, my mean would be what there? 5 times 0.1. So my mean expected successes is 0.5, which means 0 and 1 are my most likely outcomes. Now, just because I'm exactly in between 0 and 1, like that mean of 0.5, doesn't mean 0 and 1 are equally as likely. It just means they're the two most likely outcomes. And the reason why is because with a mean of 0.5, right? The reason why it ends up being exactly in between 0 and 1, even though they're not equally as likely, is because these values up here, although the probability is small, they're still going to pull the mean up a little bit, right? So it's almost like they're kind of canceling out a little bit of the influence that outcome 0 has. And so just because we're in between two values doesn't mean they have to be both equally as likely. It just tells us those are the two most likely outcomes. Okay? So notice when the probability of success is relatively low, we have this kind of right skew distribution. If we have the probability of success being exactly 0.5, here the number of trials is 5 still. So 5 times 0.5, the average number of successes will be 2.5. So 2 and 3 are the most likely outcomes. When the probability of success is exactly 0.5, it's a symmetric distribution. We end up with actually 2 and 3 become equally as likely. They're not only just the two most likely outcomes, they have the same likelihood. But then if we go to something that has a high probability of occurring, so we're keeping the number of trials constant in this top row. Well, now notice we've got kind of this long left tail, a left skew distribution. 5 times 0.9, the average number of successes is 4.5, so 4 and 5 become the two most likely outcomes. Okay? So it's kind of a nice way of kind of moving left to right there. See what's going to happen to our distribution as we go from a low probability to a high probability is it starts off right skewed and kind of becomes more and more normal, and then eventually as it gets past 0.5, we get this kind of left skewed distribution. And you can kind of see as we increase the number of trials, we just get a little more of a granular distribution. It starts to look a little bit more like a continuous. I can draw a line to the top of this. But notice, even if I increase the number of trials, my probability of success is still relatively low. I still have this kind of nice right skew distribution as well. Okay. Just kind of different visuals and thinking about, the mean, right, of these distributions. And then as we move further from that mean, right? So even if our mean is 2.5, as we move further from the mean in either direction, the probabilities decline. Here the mean would be 50 times 0.5, so 25. As we move to a number of successes in either direction, the probabilities are declining. Okay. Any questions at this point? So I'm not going to waste time with this one. I mean, hopefully, if I ask you a question like this in the exam, this should be easy points, right? As long as we have that formula, that definition in front of us, that the mean of a binomial is just n times p, and the variance is n times p times 1 minus p, right? Just a matter of pulling those in. So here, we already talked about the mean for this college example. There was 5 people, probably success is 0.3. 5 times 0.3 is at 1.5. Then the variance, we would just take n times p, so 5 times 0.3 times 1 minus p, so 1 minus 0.3 is 0.7. All right, we multiply that by 0.7, we get 1.05. And then I think if I ask you instead of the standard deviation, if you take the square root of 1.05, you probably get 1.02 here, would be my guess. So this should be like just a question you can go back to, something that looks similar to what's in the exam, but really this should be pretty easy to find the mean and the variance once we have those formulas. Right. Any questions on this? Kind of glossing over this a little bit, but I want to spend a little more time, so we have a lot more time finishing things today, so we have more time to kind of review in class on Monday. So we can go through a list of scenarios and say which one is optimal for this binomial, just so that we can start thinking about the binomial distribution and relate it to the next one we'll talk about. So which of these is not appropriate? So if I'm calculating the expected number of coin flips that come up heads out of 123 flips, well, I've got a cap, right? I'm doing an experiment 123 times. The probability of success on any one trial is 0.5, so it's consistent. And I either see heads or tails, so I have a success failure. So this is a perfect example where we could use the binomial distribution. What about calculating the probability that 5 out of 20 patients will get nauseous after taking the antibiotic, assuming the antibiotic affects everybody the same? Maybe a bit of a stretch, but for the sake of this example. Well, I've got 20 people, so I've got a number of trials, I'm capped. I'm interested in finding the probability of at least 5, and the probability that any one person gets sick is kind of the same, so I could use the binomial distribution for here. Here it's kind of weird because the success is that someone gets nauseous from this antibiotic. But remember, success failure just means what are we looking for? So we either see it or we don't see it occur, right? There's just two outcomes. Not that it's necessarily like a success if someone gets nauseous. Calculating the probability of an air traffic controller at the Muncie airport makes 3 errors per week. So what's my number of trials here? Well, 3 is what I'm wanting to find the probability of. Right, that would actually be my X. The problem is I'm looking over an entire week. I don't have any idea how many planes land at the Muncie airport, right? I don't have a number of trials that I'm being told here. So anytime we're looking over a time interval, generally that's going to tell us we should be using a different type of distribution, which is the one that we'll talk about next, which is the Poisson. Okay. So C is going to be the one that doesn't work for us here. Right? And then calculating the probability that out of 5 customers in the store, exactly 3 make a purchase. Well, if we have historical data about the probability that when someone walks in the store, they either buy something or they don't, right? We can use that as our underlying probability of success, P. We're interested in finding the probability that exactly 3 make a purchase, and we're looking at 5 customers. So the most we could see make a purchase would be 5. So we're kind of capped. So the way to really identify the difference, especially after we talk about the Poisson distribution between the Poisson and binomial, is the binomial distribution. You will have a number of trials, a capped amount of successes that you can see. If I flip a coin 123 times, I can't see it come up heads 150 times. It's just not physically possible, right? So anytime I kind of have this cap for the number of successes, then I should be using the binomial. You know, if the Muncie airport, if I knew nothing about Muncie, and potentially all of a sudden, I don't know, who knows, maybe Elon Musk or Joe Rogan moves here instead of Austin, right? So all these people come in, we start seeing this huge, people are landing all the time. Well, I could see who knows how many errors per week then, right? Like if I've got, I don't know how many number of trials I've got, kind of could go off into infinity, theoretically. So I think here I want to go through a little bit of Excel. It shouldn't take about 10, 15 minutes. And then we'll kind of spend 10, 15 minutes on that Poisson distribution. Like I said, probably finish up, do some different examples for the Poisson on Monday, and then we'll kind of use that partially as review, and then kind of jump into some other review there as well. So I've got this binomial distribution function, and I've got some slides that kind of relate to this, but it's going to open a new workbook, right? And I'm going to try to play around with this binomial distribution function. So binom.dist essentially has that nasty function with the factorials built into it, right? So all you have to tell Excel, right, is your number of successes you want to find the probability of, the number of trials, and the probability of success. And then we have this fourth thing, which is, do I want it to be cumulative or not? So we'll talk about that in just kind of after we work through the rest of it. But here, maybe I'm interested. I think the example I have in the slides is Detroit home foreclosures, right? So the number, let's say I'm interested, what's the probability I see exactly 8 out of 100 homes foreclosed if I'm just choosing at random mortgages that are held in Detroit, okay? Well, the probability that any one home forecloses in the next kind of, I think the date I looked at was like over the last year, right? Was 4.7%, so 0.047. Right? So the order of the binomial function is you tell it the number of successes you want to find the probability of out of the number of trials that you're running, and the probability of success on any one trial is the third thing you tell it, that P, right? So if we're thinking about matching it up to what we're doing in class, it goes X, N, P, okay? The fourth thing, so comma, that we tell it is, do I want this to be cumulative or not? Well, for now, we just want to find the probability of exactly 8. So this is basically like a switch. If it's 1, it switches this function on to make it cumulative. If you put a 0 in there, it just uses that binomial probability function that one time, right? Just like you would by hand. So this should spit out us the probability of seeing exactly 8 of those homes foreclosed. We get about 0.05. So I'm thinking about what I found there. The probability X is equal to 8. Okay. Any questions on that? Yeah.
Is cumulative going to be 0 to 8 or the opposite?
So cumulative. So let's say I want the probability that it's less than or equal to 8. Cumulative says start at 8, go down to 0, right? So now instead, I would have the exact same thing in this function. I'm starting at 8, number of successes, comma, out of 100 trials, comma, the probability of success or seeing a home foreclosed on any one trial is 0.047. But now if I put comma 1 as the last thing, it says, okay, make this cumulative. Find the probability of 8, but then also add to that the probability of 7 and the probability of 6, all the way down to 0, right? So start at whatever X value I'm telling you, and add the probabilities of that all the way down to 0, right? Okay. And I'll leave this here for a second because I'll show you another way we can think about this and kind of how to use cell references. So I'm going to set up over here my number of trials, my number of successes I'm interested in finding. Actually, we won't even use this, and the probability of success. So I could have used these cell references instead of putting the values in here. But I'm going to use them in a slightly different way. So let's think about, here's my different X values. Here's the probability that X is equal to that value, right? So we could see 0 homes foreclosed, 1, 2, 3. And if you ever want to set something like this up for yourself, I don't think it'll have a lot of uses for the Excel assignments we do. But if I start typing things in where they're going up just by 1, if I go down here to where this is a bold plus sign, and I right click and I drag this down, and I go to fill series, it is kind of defaults to just filling the series going up by 1 each time. So I could then use that binom.dist function. The number of successes I want to find the probability of, I put in this column over here, comma, the number of trials I've got sitting right here, comma, the underlying probability of success. And then I'll put a comma 0 here just to make it not cumulative. So I can find the probability X is exactly equal to 0 out of 100. Right? Now, if I copy this down, I want the number of successes to update to 1. So then this cell would tell me the probability I see 1 out of 100. And then when I copy it down one more, it updates it so it's the probability of seeing 2, right? So I could like build out this entire probability distribution here. Okay? Now, the problem is when I copy this down, I don't want my number of trials and my underlying probability of success to change. So I'm going to F4 or Command T on a Mac after selecting those and freeze those cell references. Okay. But if I do that, I'm just going to copy it down to here. Notice, what would my mean be? It's just going to be my number of trials times the probability of success, which of course now is so what, L3. So right, out of 100 homes, on average, 4.7 will be foreclosed. So 4 and 5 should be my most likely outcomes, right? So unless I made an egregious error, I look here, sure enough, 4 and 5 have the highest probability of occurring. And then the probabilities decline as I'm looking at the number of successes further and further from that mean. So I'm kind of seeing all this stuff play out as we're using that built-in function in Excel. And notice, one way we could check to see if this cumulative guy worked is we could use that sum function and just add up 0 through 8. Hopefully we get the exact same thing that the, putting a comma 1 did. Sure enough, we do. Okay. Now, I'm not suggesting doing it this way. I'm just saying it's kind of to prove to you that this binomial function is actually working correctly. Yeah.
Can you show, like, yeah, right, okay. I was about to ask you to show that.
Oh, yeah. No, I kind of anticipated what you're going to ask. Yeah.
So, as far as the cumulative goes.
Yep.
How would you show, like, for example, if what's the probability of like at least 8 or greater? So it's like-
Yeah. That gets tough, right? So what if I wanted the probability X is greater than or equal to, let's say 10, right? I don't have, it'd be great if they just made this like, how it was a 0 if not, cumulative 1 if it is. It'd be great if they added another one, which was comma 2, and it found the probability being greater. They don't, right? That would make life too easy. But if we know that we can find the probability of, say, 10 or below, we can always find the probability of being greater than 10, because that's just the complement. Right? So here, right, I want the probability X is greater than or equal to 10. So 1 minus the probability that X is less than 10. Well, what's the first value that meets this criteria? If it's less than 10, actually, the first one that meets this criteria would be X is equal to 9. So when I put in that binomial distribution function, I actually need to use 9 and make it cumulative. That way, this would find the probability of 9 or below, subtract it from 1. So we got to be a little bit careful with our equalities when we're using the complement rule and this cumulative binomial function. But yeah, we can do that, right? So here, the probability X is greater than or equal to 10 is equal to 1 minus the probability that it's less than 10. But the first outcome that's less than 10 would be 9 successes. And then comma 100, comma 0.047. And we want it to be cumulative, right? Because we want to subtract out, the probability X is equal to 9 and 8 and 7 and 6. And we could do that like that. Yep. Any other questions here? Just for the sake of showing you something, and I think it's interesting. Maybe it's lost on you guys. So what I had 100 homes. So I'm just going to copy this down. So I've got 100. A nice little shortcut. I think I've showed you this before, but just to reiterate it. If I double left click, it'll copy that formula down all the way to the very last kind of data point next to it. Now, obviously, like e to the negative 133, that means move the decimal point 133 places to the left. This probability is 0 for all intents and purposes, right? In fact, really, it makes sense. If the average number of homes foreclosed is 4.7, the probability if we select 100 at random that all 100 are foreclosed, that's got to be next to 0, right? That's crazy. In fact, once we get to like 15 or 16, the probabilities are already getting really, really low, right? But what we could do, if we were interested in this, is I'm going to select my outcomes and their probabilities. I'm going to insert. Oh, that's going to screw with me. What if I try doing this? This should work. Nope. Well, let's select my probabilities, and then we'll insert one of these column graphs. So this kind of shows me the frequency distribution. Now I'd have to go in, select data, edit my axis labels, and then select the outcomes here. Because unfortunately, otherwise it starts it at 1 instead of 0, but we know 0 is a possible outcome. But if you were to do this right, you could actually graph out your frequency distribution here as well, right? This kind of quickly shows you, okay, more than likely, I'm going to see some number of homes foreclosed between like 0 and 10. Anything past 10, the probabilities aren't even showing up in my graph, right? That's how low they are. Okay. So we could do something like that. I won't ask you to do that, but just something kind of to point out there. You can imagine, like, if I'm a company, like I might want to build a table like this, right? Especially if I'm trying to make projections for the future. And I'm saying, okay, what's the probability? Like, the probability that one worker gets injured or something on the job is 0.05. Out of my 100 workers, I have a real problem if 10 of them have to miss work this month because they get injured. So what's the probability I see 10 or more, right? This is really, and then I could look, or what's the probability I see no accidents this, this next month or whatever the time period is. So this is, pretty relevant to use this and kind of build these schedules, especially if you're kind of concerned if X ever went above a certain amount, right? We did the childbirth one. If the number of births in the next hour ever goes above 4 or 5, I don't have the staff to be able to handle every single one, right? So if that probability is relatively high, I'm starting to be concerned. Hopefully it's relatively low. Okay. All right, I'm going to save this and make sure I post it on Canvas. Oops, there we go. So we'll call this binomial. Any other questions on this before we kind of jump out of Excel here? Okay. Oops. Sure. I had a question up here before, but I looked at the number of people that watched it and it was relatively low, but there's a relatively low number of people that showed up here today. So for those of you that took the time out and kind of looked at that, which of the following kind of did it go over? All right, the Poisson distribution. Right? So it's actually, in my opinion, a little bit easier than what we're doing with the binomial. Right? It's the same basic idea. All the same rules. We're talking about complements and thinking about equalities being kind of a pain. All that's going to apply to the Poisson, which is a slightly different type of random variable, discrete random variable. Right? So we're still going to be interested in finding the probability of different numbers of successes, right? So we might still want to find what's the probability X is greater than or equal to 3. Right? But now, right, the probability mass function that will give us that probability changes. So the setup is going to be, we're no longer looking at a number of trials, right? We're no longer capped on the number of successes we can see. We're going to be looking over an interval. Now, for all the examples that for sure we'll probably use today, will all be time examples. I'll probably touch on this a little bit at the beginning of class Monday, and we'll look at an example that isn't time just to give you kind of an idea of what that would look like and to just get some more practice using it. But for the sake of the exam, the questions I would ask you, we're only looking at time examples. Okay? So, what we need to assume is that every interval of the same length has the same probability of seeing this thing occur, whatever it is we're interested in. We have to have no overlapping intervals. Never going to give you situations where you have to identify whether or not all these are true. We'll only be dealing with examples where all these things are true. Right? So we're still going to be interested in what's the probability of seeing a certain number of successes. It's just now, if I'm thinking about I could see 0, 1, 2, 3 successes, the probability mass function, that if I plug a 0 into it, will give me the probability to see exactly 0. It's going to look something like this. Okay? I think it's easier than the binomial because all we have are 2 things going on here. So lambda is going to be given to you in the problem. It's the average rate you usually see over that time interval. So the example of that on that YouTube video that I put up there, I think I was using the number of car crashes on a certain road over the next week. Right? On average, we can look at historical data and say on average there's 8 crashes a week. Right? That would be our lambda. We then might want to know, well, what's the probability I see 10 happen this week? So that probability, the number of successes, the probability I'm trying to find, number of successes I'm interested in, just like the binomial, that's my X. Right? So number of successes I'm interested in finding the probability of over the interval is X. The mean number of occurrences I usually see over that interval is lambda. The only other thing here, we know about factorials, but that E, right? Does anyone know what that is? E is just like a number kind of like pi, right? Yeah, it's like 2.7, 1828, 1828, blah, 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 goes off into, forever. I'm kind of this natural number here. Sometimes referred to as the exponential. Right? So you should have this button on your calculator as well. Sometimes you don't even have to hit second. Sometimes it's like a secondary button, so you have to hit second, and then it's one of the yellow things written above the buttons. But even if you couldn't find it, you can always approximate it to the fifth decimal, 2.71828. The dumbest way to remember this, I don't remember exactly what the age relevance is, but you can remember E out to like something ridiculous, like 50 decimal points with like Abraham Lincoln facts. And so I think it's 27 was the age he did his first political office or something like that, right? So 27 was the age first age he was in political office. 1828 was like, what would it have been? That would have been the year he was, I don't know, born or killed or some monumental, right? But they're Abraham Lincoln, right? 27 years old, and in 1828 he did something. Right? So that's one way to remember it, but it should be a button that's kind of built into our copy. Well, at this point, we've got everything we need. We actually have two components now. I think life's a little bit easier than with a binomial. Right? So the kind of age-old example is in this book of law. The law was small numbers. I try to pronounce his name. But this guy wrote this book. It was pretty monumental in mathematics. And one thing that he kind of realized, and one of the examples that he set up to kind of show this Poisson process, was the idea that if every year, on average, in the Prussian cavalry, 0.61 soldiers were being kicked to death by a horse, right? Either like an accidental thing. So I guess this probably we don't have like huge cavalries anymore, right? It's problems. Over that same interval, over the next year, what's the probability that exactly 3 people? Well, the average is relatively low, so even the probability of seeing 3 is probably not that high. But we could find what it is, right? Because we're going to have the average rate, or lambda, was told to us to be 0.61. We're interested in finding the probability that 3 are killed this year. So that's just a matter of lambda to the x times e to the negative lambda divided by x factorial. Now, one thing you might already be anticipating is if we have relatively large average rates, like lambda is pretty large. Let's say I wanted to find the probability that I had like 100 people died, and the average number of people killed was 61 or something. Well, remember I said the calculator can't handle anything like over 6, once I get into like the 60s. So if I start to get really high numbers of successes, I'm interested in finding the probability of. We're going to have an issue using our calculator to come up with this. But for most examples, right, we can always just make the intervals smaller. So instead of looking over a year, I can look over a week or look over a day. So I can always kind of scale it so that I can use the Poisson to find, instead of the probability that 100 are killed over the next year, maybe I can find the probability that 10 are killed the next month, right? Dealing with some actual small numbers that my calculator can. So it's the same process. Once I identify the 2 things I need, just plug them into that formula. The formula is going to spit out at me the probability, and then I'm done. So what if, so we plug these in, we get about 20. So pretty unlikely, right, given that average rate. What if I had one like this, right? So I'll have a little bit of time up here, so I'll have you guys kind of work through this one, just to kind of get some practice with this function. I'll write it up there on the board. So let's say we've got a hospital, and the average birth, was it in the next hour? Yeah, is 1.25. Right? And I want to find the probability that I see exactly 3 births in this next hour. Right? The general form of this equation is something like this. All right. Give you guys a couple minutes, kind of work with the people around you, just get some practice using this Poisson distribution equation and figure out what the probability that we see exactly 3 bursts in this next hour is, given that on average, we see 1.25. On this for a couple minutes. Yeah.
I think it's one of pretty, is that negative lambda?
It is negative lambda, sorry. It looks like it's underneath it, doesn't it? E to the power of negative lambda. And if you don't have that E, if you can't find that E button or you're having issues with it, remember, you could use that value up to the fifth decimal and get a good approximation. What about that? 30 seconds or so, and kind of talk about it. All right, so left it open. So you can always change your answer. So I think I'm a nice person, but sometimes I get spiteful. So when there's not a lot of people that show up, sometimes I like to just give away the free points. So for those of you that showed up, kind of you know, rewards you for actually showing up to class today. So, but I do want you to try to work through it, even though I'm going to do that because it's important that you kind of start to work through these and get some practice with them, right? We can talk about them, it makes sense. And then when I go to actually use my calculator, it's harder to do that. So my lambda is what? 1.25. The x that I'm interested in is 3. So 1.25 to the x times e to the negative 1.25 divided by x factorial. Even if I haven't found my factorial button yet, this is an easy one. 3 times 2 times 1. And I said if you haven't found the e button, you can always plug 2.712. Now, if we just think about this, right, what would be the most likely outcome? So here's kind of a weird one. We haven't talked about what the mean of the Poisson distribution is, but I wonder if anyone can kind of take a guess at it. If on average, we see that there's 8 car accidents on a road, then the most common number of car accidents on the road we would see over the next week would be 8, right? So actually our mean for lambda, or sorry, our mean for the Poisson distribution is actually just whatever our lambda is, whatever our average rate is. Right? So here, 1.25 is the average number of births. So what are going to be the most common outcomes that we see? 1 and 2, right? The average is 1.25. If I'm thinking about, I probably should have done something like this. Here, the mean is 1.25. Then 1 and 2 will be the most likely outcomes. And then as we move to outcomes further and further from that, the probability is going to decline. So if I'm looking at these and 1 and 2 are the most likely outcomes, 3 is not very far away from that. I'm probably not thinking that the probability is already as low as 0.01. Technically, it could be. I'm not able to perfectly visualize these Poisson distributions, but if 1 and 2 are the most likely outcomes, it seems like the probability of 3 shouldn't have already fallen all the way down to 0.01. So if I'm guessing here, I'm probably guessing B or D, but we can actually maybe plug these in to our equation, and we get about 0.09, right? So 0.09 there, 0.093. Right, round to the second decimal is 0.09. So it's still open. So hopefully everybody gets this one correct. Right? Yeah.
You can't do a complement on this, right? Because there's no class.
I'll give you an idea about that in just a second. So everybody after answering for this, before I kind of, because I do want to do that before we leave today. All right. What about, I have the same setup, but I want the probability that I see at least 3 births. Is that kind of what you're getting at, right? Because it's open-ended. I guess technically, maybe I'm limited in like the population but like, for all intents and purposes, this number of successes goes off to infinity. Excuse me. So if I try to find all the X values that fit this criteria, the probability X is equal to 3, plus the probability X is equal to 4, plus the probability X is equal to 5. Well, when do I stop? Well, what could I do here? If this is A, I know that the probability of A is equal to 1 minus its complement. So here the complement would be that X is less than 3. Kind of similar to the binomial stuff. What are all the outcomes that fit this criteria? X is equal to 2, plus the probability X is equal to 1, plus the probability X is equal to 0. Now I can use that Poisson distribution equation 3 times, add them all up, subtract them from 1. So it's a little bit, it's kind of the same idea as what we're doing with a binomial, but you're right, it can't work like in the opposite direction. So like, let's say I wanted to find the probability that I see less than 10 births. I can't do like 1 minus the probability it's greater than, and it makes my life easier. I actually have to just start from 10, work down to 0. If I'm doing a less than. Okay, that was a good question. So we can use that complement rule the same way we were with the binomial, but do it for the Poisson. Okay. We could do 2 or more births. This is the same idea of what you just asked, right? I think I used 3 over there, right? So basically just changing it from 3 to be greater than or equal to 2. And it'd be the same process. So if we wanted to do that, right? Probably X is greater than or equal to 2 is 1 minus its complement. There's only 2 criteria that fit this, right? There's no equality. The first number less than 2 would be 1. Right? So the probability that X is equal to 1 plus probability X is equal to 0. Subtract those from 1, and we can get our probability here. So yeah, it is a problem. If we want it probability is greater than something, it's open-ended. We don't know when it stops, so we're going to have to use that complement. Any other questions at this point? And a lot of times I'll do something like this, because if you notice, anything to the 0 power is just 1. 0 factorial is 1. We can essentially ignore 1s. Multiplying or dividing by 1 doesn't change anything. 1.25 to the first power, any power to the first, or any number to the first power is just itself, so 1.25. And then 1 factorial there is also just 1. All right, so this one actually computationally, if I'm able to recognize those very easy things, right? This is 1, this is 1, this is 1.25, this is 1. Now it's really a lot easier to enter in my calculator than it might have originally looked. So we'll stop there for today. I've got a couple more things just to talk about with the Poisson. I'll show you a slightly kind of different example. I'll kind of leave you on the great stats meme, which is, oops. Have you heard the joke about the Poisson distribution? It's pretty fishy because Poisson is fish in French. All right, I tried. So I will see you guys on Monday. We'll finish, do a little bit of Poisson examples, and then we'll start doing practice exam reviews. Okay. So we didn't have time to do that formula sheet stuff. But what I'll start out walking through it on Monday. Basically, I think a good way to study is have that formula sheet and try to write down next to every formula like what it is. Like this is the mean. This is a weighted mean. This is the addition rule with probabilities. And that way, when you're studying, like you have the words there. But then when you just see the regular formula sheet without the words, like it's kind of like that memory, like you'll be able to almost visualize, oh yeah, I remember that being there, I remember that. And it'll help you kind of use that formula sheet as you're studying, so they'll just kind of cement like what formulas we're going to, what types of problems.
So we can't bring the formula sheet to the
No, so I give everyone the same formula sheet to start off the exam.
Okay.
Yeah. Yep. I dropped the 3 lows.
Yeah, I was trying to purchase it, man. I try to ask him to work with me, and So.
Okay.
I'm gonna have to just,
If you can't find like a physical one, you can download the app, the iClicker app. Or I told a student a couple weeks ago, just they got on and got one on eBay. Like you can find some for like $20 or something. Yeah,
Okay.
yeah.
and, about the exam,
So
I've seen it in the announcements.
yeah, so there's a folder on the files tab. And it's called like exam 1 practice materials. It has 2 practice exams with the answers. So you can like make sure you know how to work through them and then get to the right answer. And then it has kind of the formula sheet that I'll give you for the exam. But those practice exams would be the first thing, but also probably the second thing I do. Right? I really go on over those because they're really good
You say
representation.
you should practice exam first?
Yes.
Okay.
Yeah, first and foremost. I mean, those
Okay.
you should really like. The only way I'd start moving on to other things is if you feel really comfortable with all the questions in the practice exams.
Okay.
Really focus
All right.
on being good with those.
All right, I'm gonna try to get that iClicker thing.
Okay.
Try to get that figured out, man.
Yeah, I dropped the 3 lowest, but yeah, you'll want to get that figured out. If
Yeah,
you're
for
having
sure.
issues, let email me and we'll
Yeah.
try to figure something out.
Okay, thanks, yeah, I appreciate that, man.
Because I actually have an extra one in my office, so
Really?
I can bring it to class for you. But you know, if you're late or something like today,
Yeah,
but
yeah.
I'm not. It's okay. But I'm just saying, like, if that's the route we go, then like
Oh, yeah, I'm not.
I would have to give it to you ahead of the class.
Yeah, I'm gonna try to start making more time. See, I drive 30 minutes from Anderson. and,
Oh, okay. Okay.
Yeah, so I'm gonna try to make it on time. I'm
Yeah,
gonna try to
yeah.
start, but
Okay.
man, it's just right now that's
That's tough.
the iClicker. Yeah, that's what I was like, man, if I don't have the iClicker, then
Yeah, yeah.
I'm trying to get that. and then-
Okay. Yeah, like I said, I'll start bringing that with me. So if you're here at a
Yeah.
class and you'll have it, I'll just kind of give it to you.
Yeah, I
for the
appreciate
class.
it.
Yeah, yeah. I'll throw it in my laptop bag as soon as I get back to my office.
Okay, I appreciate that. All right.
Yeah.
I got a big favor to ask.
Yeah.
What if you can't accommodate? Well, do you have office hours on Tuesday?
Yeah.
No. I take my test. the day
On Tuesday?
before.
Oh, yeah. Yeah, actually, send me an email so I don't like have something I'm forgetting about. But really, any day, any time of the day on Tuesday, probably between like 10 and 4, I can make work. Just shoot me an email and yeah, all right, set up a time. And I'll have like so next to my office, there's a room. It has like the printer in it, but it's pretty big. No one ever uses it. So I just set you up in there and I'll be like 2 doors down. That way it's not weird for you to like sit there in my office and have to, you know, but yeah, shoot me an email. We can
All right.
set up a time that works.
Thank you very much.
Yep.